Hey guys, we just finished off our lesson on balancing chemical equations using stoichiometry. What a great word. So now what we're going to talk about is we're going to start to talk about stoichiometric coefficients and how we're going to use those to determine excess and limiting reagents. So basically when things react, right, like we in the lab, like we'll take a particular amount of a substance and we'll react that, and then we'll have a particular mass of product that is produced. And practically that's how things are, like the easiest way for us to work it, right? Like it's not easy for us to measure moles in the lab. It's easy for us to measure grams because we have scales that can do that. However, when things are actually reacting, they're actually reacting in molar ratios. They're not reacting in mass ratios, right? So we have to go through and we've actually got to work out the number of moles of each reactant and the number of moles of each product that are being produced. Okay, so a stoichiometric coefficient is simply just these big numbers that are out the front of each of the chemical species. So that's the stoichiometric coefficient. The stoichiometric ratio, or the molar ratio, is just the ratio of each of those compounds. So we've got 2 moles of C8H18, we've got 25 moles of oxygen gas, we've got 16 moles of carbon dioxide gas, and we've got 18 moles of water that's being produced. Okay? If there is a limited amount of one reactant, so let's say we only had 1 mole of this, then we would only be able to produce half the amount of carbon dioxide and water at the end. Similarly, if we have an excessive amount of one, so let's say we have like 50 moles of C8H18, but we've only got 25 mole of water, then this is going to limit the amount of the reaction that can produce. Okay, so let's do an example. We've got silicon nitride, and that's made by combining silicon and nitrogen gas at high temperatures. Determine how many moles of silicon nitride will be produced in this reaction. So the first thing I need to do is I need to actually make a chemical equation. So we're going to do this by just writing out each of the chemical species. So the first one is silicon nitride, and I think that this is a solid. So silicon nitride, and we're going to assume that's a solid, is made by combining, oh, I should have done this the other way, shouldn't I? Made by combining silicon, and I'm going to assume, I think silicon's a solid at room temperature. I'm not 100% sure. And nitrogen gas, and it's at a high temperature, so maybe this is in a gaseous form if this is at high temperature. Anyway, determine how many moles of silicon nitride will be produced in this reaction. So effectively all we're going to do now is we're going to balance our equation. So just like we did before, we're going to make up a little table. So we've got silicon and we've got nitrogen. And on the left-hand side of my equation, I've got 3 silicons and I've got 4 nitrogens. On the right-hand side, I've got 1 silicon and I've got 2 nitrogens. So this is going to be a nice simple equation to balance. So I'm going to double the amount of nitrogen on the right-hand side, and then I'm going to triple the amount of silicon on the right-hand side. And now I have a balanced equation. So how many moles of silicon nitride will be produced in this reaction? If I have 3 moles of silicon and 2 moles of nitrogen gas, then I'm going to produce just 1 mole. Now we wouldn't write the number 1, but I'm going to produce just 1 mole of silicon nitride. If I wanted to write this as a molar ratio, I could write this in the ratio 1 to 3 to 2 for silicon nitride to silicon to nitrogen gas. Okay, the next question here, determine how many moles of silicon are needed to react with 4 moles of nitrogen. So assuming I don't actually have 2 moles of nitrogen, assuming I've actually got 4 moles of nitrogen, I've actually doubled the amount of reactant that I'm going to be using. So that means I'm going to need double the amount of silicon, and it also means that I'm going to produce double the amount of silicon dioxide. So that's going to be 3 moles of silicon were needed, so now we need 6 moles if we're going to double that reaction. Ooh. Similarly, we're going to produce double the amount of product, so 2 moles of silicon nitride. All right, so what I want you to do is I want you to have a go at this question here. So consider the reaction between barium nitrate and water to produce barium hydroxide and ammonia. Ammonium. ammonia is the NH3 version. Ammonium is when it's NH4+. Okay. All right, so calculate the mass of NH3 produced if 220 grams of barium nitride reacts with excess water. So if you want to have a go at this, pause the video now. I'm about to go through the answers. So the first thing that I'm going to do is I'm going to convert everything into moles, okay? Because we don't work with masses, we work with moles. So first of all, I need to convert this amount into molar mass. So I've got NH3, and the information I know about NH3 is I know, oh, no, I don't know. I don't know what the mass is going to be. I don't know what the number of moles is. I could actually work out the molar mass though, without having to look at the question, because I can do that using my periodic table. So the molar mass of nitrogen is going to be 14.01, and the molar mass of hydrogen is 1.01, and I've got 3 of those. So the molar mass of this compound is going to be 17.04 grams per mole. All right, let's see if we can do something similar now with the other compound that we've got. So 220 grams of barium nitride. So we've got Ba3N2. Now we know that we've got 220 grams of this. We don't know how many moles we have yet, so that's what we need to rearrange and work out. And we can work out the molar mass. So barium's number 56 on the periodic table, and it weighs 137. So we've got 3 lots of 137. 0.33, and then we also have 2 lots of the nitrogen. So remember, nitrogen weighed about 14, so we've got 2 lots of, excuse me, I'm trying to do this on the calculator and talk at the same time, 2 lots of 14.01, so that's going to give me a molar mass of 440.01 grams per mole. Okay, so we can actually use that molar mass formula to work out the number of moles of barium nitride. So we can rearrange the equation so that we get the number of moles is equal to the mass divided by the molar mass. So that just comes from this original equation, and all I've done is I've just rearranged it to get it in a form that's actually going to be useful to me. All right, so let's substitute in the values that we know now. So the number of moles, and I'm going to write in brackets here, just so I know which compound I'm talking about, is going to be equal to 220 grams divided by 440.01. I'm just going to round this to 440 just to make it easy for myself. So this is going to be 2 moles. So 2 moles of barium nitrate is reacting with an excess amount of water. Okay, so in this initial reaction, we can see we've only got 1 mole, and again, we're not going to write the number 1 out there, but we know we've got 1 mole of barium nitride. Now, in this case, we're saying we've got 220 grams of it, which would be effectively 2 moles of this. So we've got 2 moles of this is reacting with an excess amount of water. So what is the mass of NH3 that's going to be produced? Okay, so since I've doubled this and we've got an excess amount of this, it means I'm going to double the amount of ammonia that's being produced. So it means I'm going to have 4 moles. So now we know that I've got 4 moles of ammonia. So what I'm going to do is I'm going to substitute it into that formula, and I'm going to rearrange, and I'm going to work out the number of moles of NH3. So molar mass is equal to the mass per mole. I'm going to rearrange this now so that the molar mass times by the number of moles is equal to the mass. Now I'm going to substitute the values that I know into my equation. So the mass is going to be equal to, I'm just going to be pretty rough with this, 17 times by 4. So 17 times by 4 is going to give me 68 grams of ammonia. Okay, so how did we go? Did we get it? A little bit tricky, easy, hard? I don't know. You've got to let me know. So what I want you to do now is I want you to have another go, and I want you to do question 3 on your own. I'm going to come back and I'm going to show you how to do the solution for this question. Okay, so 120 grams of propane, not protein, is burnt in excess amounts of oxygen. Calculate the mass of water produced. And they've already got a nice balanced equation there for us. So let's start off with writing what information we actually know. So we've got an excess amount of oxygen that's being reacted, and we are producing water. So we've got the mass of propane is going to be 120 grams. We can work out the molar mass by going to our periodic table. So we've got 3 lots of carbon, and I'm just going to be very rough with this. So 3 lots of 12 plus 8 for the hydrogen, and that's going to give me 44. So I've got 44 grams per mole of propane. All right, I'm going to substitute that into my formula now. So the number of moles is going to be equal to the mass divided by the molar mass. So again, that just came from rearranging that equation. So my number of moles of this that's going to be reacting is 120 divided by 44. So 120 divided by 44 is about 2.7. So 2.7 moles. Okay, so as you can see here, we've got 1 mole of this is reacting to produce all of this, and we've got an excess amount of oxygen. And you can see that we've actually got 2.7 moles of this, so we're going to multiply this entire equation by 2.7. So that means we're going to multiply 4 by 2.7 as well, and that's going to give us how many moles of water is being produced. So times that answer there by 4, and I've got 10.9. So I can write the number of moles is equal to 10.9 mole. Okay, I also know the molar mass of water. So the molar mass of water, again, we're just going to be rough with this. Oxygen is 16, hydrogen, we've got 1 each, so it's going to be 2. So we've got a total of 18 grams per mole. So I'm going to substitute that into my equation. So the molar mass is equal to the mass per mole. And I'm going to rearrange that to get the mass. Okay, so then the mass is going to be equal to 10.9 times 18. So chuck that in my calculator, and I'm going to get that the mass of water produced is 196. Oh, I'm just going to round it to that, 196 grams. Okay, a couple more to go. So again, if you want to pause the video now is the time. Okay, so this one here, what we're going to have to do is we're going to have to write a balanced chemical equation first. So what chemical species do I have? I've got iron 3 chloride. How do I know this is iron 3 chloride? Well, because chlorine I know has a charge of -1, and I've got 3 of them, right? So to balance that, this must be 3+, okay? All right, so if I've got iron 3 chloride, I'm assuming that's a solid. I'm assuming we're working at room temperature, and that reacts with 52 grams of hydrogen sulfide. And again, I'm going to assume, whoops, not a gas. I'm going to assume that this is a solid, okay, because usually this is an ionic compound, right? So this can dissolve in water. When it's dissolved in water, it's actually an acid, becomes acidic. So if it is 52 grams of it, I'm assuming it's going to be in the powdered form. And that is going to produce iron sulfide. Now, remember with iron sulfide, to balance this has a charge of 3+. Sulfide has a charge of 2-. So I'm going to just swap and drop. So Fe2S3. And then I'm assuming that's solid as well, sorry. And then that's going to produce hydrochloric acid. Now, hydrochloric acid generally means it's going to be dissolved in water. This could also be the powdered form, not 100% sure. Doesn't matter for the point of this. We've got to balance the equation. So now let's just have a look. So this one's a little bit more complicated. I'm going to write out my table. So I've got iron, I've got chlorine, I've got hydrogen, and I've got sulfide. You know what, guys? I've just gone ahead and I've just balanced the equation, and I've realized I've only got about a minute left. I've only got 15 minutes to do these videos. So I might actually stop this video here, and I'm going to keep going through how to find the limiting reactant and the mass of iron sulfide produced in the reaction. And the last question I want to go through for this chapter is question 6. I normally wouldn't spend so much time doing so many of these questions, but I think this is such an important thing because it's a basic skill that you are going to use in chemistry. Whether throughout grade 11, throughout grade 12, throughout all of university, even if you are just doing a science degree and you're moving on to biology or whatever, or if you're doing medicine, you will still have to be able to balance equations. So I do want to go through in more detail how to do that. And you really need to be confident with that molar mass formula. So I will make another video. I'll see you in the next one, guys. Sorry about that. Didn't mean to cut you off. I'll talk to you soon.